Thank you so much. And yeah, I'm a man, but I'm not Amanda. Amanda is at the back there, and I just want to say thank you, Amanda, for giving me the opportunity to speak here. We discussed the content, and it turned out that a lot of what we wanted to talk about is stuff that I've been working on, hence here I am. Also want to say that I read a study recently that said that parole officers, or parole was far less likely to be given just before lunch. If your parole came up, say at 9 o'clock in the morning, the judge would be far more likely to let you off than at 11:30. So when you're looking at me and judging me, bear in mind that part of what you're thinking is affected by the fact that you need some food. Okay, so data integration and error, big data from the 1930s to now. So yeah, there was big data in the 1930s. Not many people know that, but what we learned from big data in the 1930s, or what our ancestors learned, is still relevant now. I'll talk about television measurement, one of the fundamental things that Nielsen does, and return path data that's now available from set-top boxes that can help us in that, and then talk about some questions around understanding error on data integration and so on. So, big data 1930s style. I've presented this slide a few times, and I generally offer a bottle of champagne for anybody who can name the person on this slide, but I'm not going to do that now because I know that Amanda knows who it is. But does anybody know who this person is? Okay. This man is Alf Landon, and he was predicted by the Literary Digest to be the next president of the United States in the 1936 election. And the Literary Digest based that on big data. They had returns from millions of their readers saying who the readers were going to vote for. They'd done the same thing in 1932, and they got it right, and they went bigger and better in 1936, and confidently predicted that Alf Landon would be the 1936 president. Now, I don't know if you've checked, but he wasn't. FDR ended up being the president. The Literary Digest published this cover, Is Our Face Red? And it definitely was, and they actually went out of business because they had such a loss of confidence from advertisers because they really messed up. And that was based on millions and millions of data points. So how could they possibly have got it wrong? The simple answer, of course, is that Literary Digest readers were pretty upmarket. If you could afford the Literary Digest, you were more likely to be better off, and you were more likely to vote Republican than Democrat. So it was a simple case of bias. Meanwhile, Dr. Gallup, and you can see Dr. Gallup there on the left and Art Nielsen on the right. Dr. Gallup predicted with 50,000 interviews based on a scientifically representative sample that FDR would win. And that was a really seismic event because it really gave underpinning to the market research industry, the media research industry that I've worked in for 25 years, and now it was a really, really big industry. But it's all based on that foundation. But if you want to do research, you've got to do it in a scientific way. You can't just get any old data and think that it's meaningful. So early days of research, there was a company called Mass Observation in the United Kingdom, and what they did was they went out and they just spoke to people in pubs, which probably quite a fun job to do, but not particularly scientific. I think they were set up by a filmmaker, an anthropologist, and a poet, and that's the sort of research they were doing. And it gives you a very interesting insight into Britain in the 1930s, but it doesn't give you anything in terms of hard statistics. So it was really about 1936 election and the advent of companies like Gallup and Nielsen putting some sort of scientific basis into measurement that was the foundation of where we are now in research. And then since the 1950s, things have got a little bit more sophisticated. You don't just do a sample and take it at face value. You look at possible biases and you weight it. Probability models have been brought into the equation to help with understanding consumer trends and so on. A lot of imputation techniques, data fusion, time series analyses, and so on. And now, really in the last few years, hybridization, as we've been calling it, where you take samples that are representative of the population, and then big data that may be a census of a particular area of the population, put those two things together. So Nielsen was founded in 1923, and in 1950 introduced TV audience measurement. We'd been measuring consumer products and radio prior to that. Nielsen ratings are the currency for US TV advertising, about $65 to $70 billion worth of advertising on television based on what our panels, say our measurement panels that give the TV audiences. So it's really fundamentally important that that research is valid and accurate. So how do we do it? Currently we use people meters, an electronic measurement where every television set in the household and cable boxes and DVRs attached to the televisions are all measured using Nielsen meters, and we ask people to register their viewing when they're watching the TV. And we generate probability samples to do that. The television panel in the United States is about 20,000 households, approximately 60,000 individuals, and visitors in the home as well, also being measured. So that's how we currently do it. Because what's happening with TV is more and more fragmentation of viewer choices. This is a Dish Latino channel guide. So that's just on one platform for Hispanics. These are the channels that are available. And you can imagine there's lots of different platforms, a lot of different cable operators, a lot of viewing on other devices now, on mobiles, tablets, and so on, and increasing population diversity. So everything's getting more complicated. The positive side of this, though, is that more data are becoming available because as people watch on devices, information comes back from those devices. That includes set-top boxes on cable boxes and also mobile devices and PCs and so on. So where are we going with our research? The statistical tools are changing. We had really, since the 1930s, a very sort of simple statistical model to measure the population. You sample it, you measure it, and then you project it. And that's pretty easy to understand. But now we're getting more complicated. We still need that, but we also are now integrating other data sets with panels, using data fusion methods, probability modeling, calibration, and so on. So it is getting more complicated. But at the end of the day, we still need to be mindful of getting it right and not making the sort of literary digest problem. So set-top box data, what can that give us? Well, it gives us large, what you might call convenience samples, but actually, in a way, convenience samples is probably not quite the terminology for it to be fair. It's more, you get what you get, and you probably know what it represents. It may represent a particular cable provider's set of boxes in a particular market. So you do have a definition, where sometimes with convenience samples you don't. You just kind of get whoever you can, and you don't really have any sort of fundamental design understanding. But what we're looking at with set-top box data is potentially in a market where we may have a panel of, say, 1,000 homes, there could be millions of boxes providing information. And that clearly gives us a level and scale of data that can give us much more stable results. However, if we're in a position where a market could be, say, New York, where you've got several million households, and if you've only got 1 million of those giving you set-top box data, that 1 million may not be representative of all the households. And so on its own, it's not going to be enough. So we look at combining the set-top box data with panels to give us stable but also unbiased research. And here are the gaps and biases that exist with set-top box data. The data quality is an issue that we need to be aware of. I've got a slide coming up about that. The coverage, as I've just mentioned, you may have a lot of boxes that represent one particular part of the market, one particular set of customers, but not everybody. Sometimes the data may not be as timely as we'd like it. Our clients are used to getting overnight results for TV ratings. And the samples may, for set-top box samples, may not therefore be fully representative. First sort of modeling problem we face is TV set activity. You may know that the set-top box is tuned to a particular channel, but that doesn't mean to say that anybody is watching it. If you checked out the set-top box data from my house, it would appear that I watch Comedy Central from 11 o'clock at night during the week, all the way through the night. I don't. Generally, Colbert Report, and then I'll turn it off. But I don't turn the box off, I turn the TV off. So we need to address that. Household characteristics. We may know what the boxes are doing, but we don't necessarily know what the household is. We can get some good insights from tuning events. So if there's heavy Hispanic channel viewing or heavy kids viewing, it gives you an idea about the demographic composition, but typically that data is not available directly. And it is tuning information. It's what the boxes are doing. It isn't what people are doing. And at the end of the day, advertisers are interested in reaching people as our program makers. So we need to model for persons viewing as well, including people who may visit the home, not just people who live in the home. And then there's other viewing activity on other sets that may not have return path capability with set-top box data unavailable, and then all these other devices that people are increasingly using. Plus, of course, all those homes that are not covered by set-top box data because maybe the data isn't available, or maybe just the digital return path capability isn't there. So a lot of challenges. Now, the concept of total survey error is one that we always have to be mindful of, I think, when we're looking at integrating these data, because we've got, with set-top box, the potential for much reduced standard error because we've got much larger samples, and that's really the benefit. But because of all the issues I've mentioned, we also have the problem of bias. With our people meter samples, it's the other way around. We have potentially large standard error because the samples are not as big as we would like them to be because of economic factors. But the bias is acknowledged to be very low because we've got a complete measurement. So putting those two things together should give us the best of both worlds. But this concept of total survey error is, I think, a fundamental one for us to determine whether we're improving the measurement. So some examples of set-top box data quality. On the left, what we've got is you can see those little spikes, and those are spikes of about 2% of the population changing channels at program junctions, and that's fairly sort of standard and what we'd expect to see based on what we know about TV viewing, so that's fine. But on the right, you can see a big spike there at night, and it wasn't an earthquake, it wasn't like the data we just saw before. This is machine reboot activity, where the cable provider is downloading information, and it looks like something's happening on the set-top box in terms of somebody viewing it, changing channel, and so on. But of course, nothing like that is happening. It's just a machine-generated activity. So just an example of the sorts of things we have to address. So at the end of the day, and you know, as I was saying about total survey error, are we improving the measurement? Well, we have to be very transparent, and we have to validate at each step and overall, and we have to have some sort of statistical rigor. And what we're seeing here is a comparison of overall ratings for women 18 plus for Monday to Friday in November 2010. And pretty stable when we're comparing our people meter, the blue line, with our hybridized measurement. But you can see there is a bit of a gap there that I've highlighted. And what we found with that is that it was not statistically significant. It was close to being, but it wasn't quite statistically significant. But what we're doing with this is we're assessing for each sort of pair of data points whether we do have statistical significance, and then looking at our overall distribution to see whether what we've got with our hybrid measurement appears to be representative of the population. And again, the total survey error concept here for females 18 plus, we've got a reduction in our total survey error as we move to hybrid of 19%. For females 18 to 34, 38%. And this is where you see more gains with the smaller demographics because the sample sizes are smaller there. So clearly, there's benefit here to doing this, and we've demonstrated it through a sort of statistical process. So that's it on set-top box. I now want to talk about broader issues of integration errors and various things to discuss, input error, matching error, and so on. And I'll get straight onto them. So input error, garbage in, garbage out. Not much you can do about that. If the data isn't there, or if it's wrong, or it doesn't quite give you what you want, then data integration doesn't normally solve that problem. Other than you can sometimes get improvements through integration weighting effects. An example may be that you have a data set that is not very good in terms of representing young adults because they're difficult to recruit to a survey, for example. So when you look at your overall measurement of, say, 18 plus individuals, that affects the results. Now, clearly you can solve that through a weighting technique just on its own, but you can also solve that almost immediately through integration if you're then fusing that data set onto a representative sample. And this is something we see quite a lot with our data fusion business where we're taking our television panel data and we are fusing information onto it. Our television panel is a very good, solid, representative sample of the population in the US, and by fusing data onto it, we're changing that fused data and making it more representative. Now, clearly, there's only so far you can go with that. If you've got a really, really bad sample and you don't have, if you have a tiny percentage of, say, young Hispanics and you're interested in young Hispanics, you're not going to solve the problems just through that sort of weighting. But in most cases, you find you're in a reasonably good position to mitigate errors. And I think this is an important point because I think a lot of people say, well, if the data is what it is and it doesn't get any better through integration. Well, it can do because it can, you can approach it in a slightly more rigorous fashion. Now, I want to talk about matching error for address matching because this is increasingly an area that we're getting involved with, and it just seems the whole industry, the whole media industry and related advertisers are getting involved with taking very large databases, maybe customer relationship databases, and then matching as much as they can on a name and address level. And we've done quite a lot of that in various parts of our business around advertising effectiveness. And what we find is that from a marketing perspective, this works really well because you just go to a client and say, we've got single source data. But it isn't really single source data, it's address match data. And you don't always get a perfect match. And I like to think about sort of the good, the bad, and the ugly. And the good, obviously, is when you get a correct match. The bad is, well, you didn't get a match at all. But the ugly can be when you get an incorrect match, when you think you know something about a home or an individual, but actually you don't because you've incorrectly matched. Excuse me. And what you get there, though, is a trade-off between match rates and error rates because it's also not necessarily a simple equation of this is the exact address and the exact name. There's maybe some slight difference, then you have to make a decision whether it's sort of close enough. Is it a sort of 90% match? And will you accept that? In doing that, you're going to get more matches, but you introduce the possibility of incorrect matches. One thing I would say, though, is that if you go into multiple database integrations, I don't think that the error rate, say you had a 90% match rate on one match and you get another 90% on another, doesn't necessarily mean to say that you've got a sort of 80% match overall. What you may find is you've actually missed 10% of the population who aren't covered on either of those databases. So you just have to be sort of conscious of what you've got and understand the databases and their limitations. It's difficult to be very sort of to definitely say that there is a multiplicative effect. So that's matching error on names and addresses. A lot of what we're doing, though, is more statistical imputation, where we're matching on a set of common characteristics that may be, say, demographic or media-based or purchase-based information. And in doing that, then you can introduce model bias, leading to what some people call attenuation, others call regression to the mean. But when you're looking at any individual data point, that bias that the model has can be undetectable just because you've got sampling error, and so there's a level of noise around that. And this chart sort of gives an example of that. And what we've got here is 1,000 product category users analyzed in terms of their total hours of weekly television viewing. And I've sorted it by the truth, the actual data. And then we've done a fusion test to see how good the fusion is at predicting those hours of viewing. So the pink line is the actual data going from the lowest product use of about 20 hours per week to the highest one, around about 35 hours a week. And then you can see the blue fused data, and it's bouncing up and down. And that's because we've got samples, and we know we're not going to get it exactly right. What we're trying to do is estimate what the population does. And there's clearly some sampling error around that. But what this shows is that the fusion works pretty well. It does track the pink line pretty well. And if we put a best fit through it, which is the yellow line, you can see that it's pretty good all the way through, apart from right at the left-hand side and right at the right-hand side. And that could be some evidence of regression to the mean there, where the lightest viewing is not quite as light in the fused data, and the heaviest viewing is not quite as heavy, so you've got a little bit of attenuation going on there. But as I say, you look at any one of those 1,000 points, and you wouldn't necessarily conclude that it was biased. It could just be by chance variation. So how do we get around that? How do we estimate bias? Well, what we do is, for each of those pairs of points, we calculate a z-test and compare the real and natural, and then we look at the distribution of z-scores, convert those to probabilities of occurrence, and then compare them with actual. And what we've got here on that pink straight line is the fact that we would expect that one observation to be difference at the 1 in 1,000 level, and 2 at the 2 in 1,000 level, and so on, because we've got 1,000 observations. So we get a straight line. But what we've actually got is a slightly broader spread, which is the S shape. And that gap between the S shape and the straight line, that we can assume to be the bias that we've introduced into the measurement. So that's typically how we do it. As I say, it doesn't tell you for any individual point that you've got it wrong, but it does give you some overall feeling of the error that you've introduced. Now, when it comes to integrating multiple data sets using statistical techniques, fusion, imputation, and so on, there are various ways that you can approach it. And I've got 2 ways here, the hub and spoke approach and then a sort of sequential approach. And what we've got here, based on a single source data set we have of our people meter television data, internet data, and credit card purchase data, is, first of all, on the left, we're fusing the web use onto the TV panel, and then we're fusing the buy purchase data from credit card data separately onto it. Whereas on the right, we do the same thing for internet, first of all. We just fuse the internet data, but then when we're doing the fusion of the buy data, we're also taking into account internet usage that we have on our buy data set, and using that. So we're fusing both to the TV and the internet data simultaneously. And when we do that in this test, the accuracy clearly improves, and the correlation between internet usage and purchase data improves from 0.4 to 0.5, and our overall correlation between TV and internet and buy goes up from 0.44 to 0.67. And we're making best use of the data here because we are taking into account all the information that we've got from the internet data when we're fusing the buy data, and you can see that it's improving it. This is early days of this test. We're just working through this. There's a lot more we need to do, but I think these are indicative of the sorts of things that you would expect to see, that you really want to try and use all the data that's available to you when you're doing fusions like this, and you do get improvements. So if the hub data, in this case the television data, had all the relevant linking information, then it wouldn't make any difference. But in this case, because we're adding in the internet data and then subsequently using it in the sequential fusion, we get a better result. The problem you find with this, though, is that it kind of works well for 3 data sets, but the moment you start to move beyond that, then you need to be very careful. Things turn into a bit of a mess because there are so many intracorrelations that you need to be concerned about, and so care needs to be taken, I think, when you're doing something like that. Okay, just about running out of time. Validity levels, individual versus aggregated. Won't dwell on this because of time considerations too much, but a very important consideration here is individual level predictability versus aggregate level. And a lot of what we're doing works at the aggregate level, but it doesn't work particularly well at the individual level in terms of a perfect prediction of whether somebody does or does not use, say, a particular brand of shampoo. But what you can do is predict viewing levels of that particular brand's users. So that's the sort of difference. That said, individual prediction, even if it's not perfect for all uses, it can still give you improvements. So we do work with precision marketing where we're getting 40% improvement on random when predicting product users based on cookie prediction. So what does that mean? It means when an online advertiser advertises they're reaching, say, 14% of that of those product users, or 14% of the cookies they're targeting give you those product users, whereas they would have had 10% if they hadn't done it. So it's worthwhile doing that, and that can lead them to win in bids for programmatic buying by say, bidding 30% higher. There's an arbitrage there, where they're getting 40% gain for 30% extra cost. Okay, so in conclusion, there does seem to be data everywhere at the moment. That's a great problem to have. The data quality and relevance is essential now as it was back in the 1930s, as is statistical integrity. And obviously you can get insights from all this stuff, but you can also get error. And that's clearly something we all have to be conscious of, and remember Alf Landon. Okay, that's it. Thanks very much.